And now it is my pleasure to introduce Micron Tool Sales Director, Clive Komlenik, whose mechanical engineering background and industry knowledge will serve you well today. Clive?
Thank you, Dennis. Happy to be here. Welcome everyone to this webinar. We're going to have a lot of fun here. Hopefully, as we discuss titanium, the challenges that we see in the market currently are innovative solutions to what we have going on, and go through a little bit of a learning session here. So let's see, start the slideshow. All right. I don't want to lose the webinar. Hopefully that's not going to be a problem. All right, so kicking off, welcome again. Dennis, thank you for having us here. Like I said, we're very honored to present this. My name is Clive Komlenik, work as the sales director for Micron Tool on the East Coast. My key projects day in, day out is leading our sales team, as well as introducing our new innovative solutions to the market, working with our key customers and spending time at the spindle. The running knowledge about me is the more time I'm actually next to a machine and less time I'm at a meeting room, I'm a happier camper. So I hope to be able to meet you guys all in person after this, or at least some of you, and actually run some tools with you. So as we go through here, please keep in mind, this is a webinar for everyone's benefit, right? So I can listen to myself talk all day. If you have any questions, make sure you submit those in the chat. We'll address those at the end. As Dennis said, he'll be moderating the Q&A session after we go through. But in the interim, if you have something on your mind, please put it on the chat so we don't forget, and we're able to address it at the end of the webinar. What we're going to be talking about today is titanium, right? This is a up-and-coming material. It's one of the most abundant materials in our world, though everyone attributes it to a high price, high cost, and high performance, which is good, but we see it entering the marketplace more and more, from everything from consumer goods to medical implants to the aerospace sector. Right. So as we break down what titaniums we're manufacturing with, we take a look at tooling specific for those materials. As this material becomes more prevalent, I think it's going to be challenges that we're going to be running into more and more in the coming years. So Micron Tool is happy to introduce 2 specific lines of titanium drills specifically for the material. As we get into it, we're going to be looking at some basics of drilling, the good formations of chip formation, consistent torque values, what makes a constant process work, what the challenges are with titanium, and how that affects the current tooling on the market. And then we'll get into a little bit of the specific performances of our solutions and our tools. All right, so chip formation. Why is this important, right? Chip formation really is the fundamental starting point for all drilling, for the consistency that we need. It's something that we must be able to work around, work with, and control in such a way that we're going to be able to sustain a constant process. As I noted before, titanium is an expensive alloy. This doesn't come from the abundance of the material, but the processing that it takes to actually make either commercially pure or alloy titanium. So in this facet, as we see expensive parts, expensive material, we have to have a reliable process. In order to sustain a reliable process, we have to manage good chip control. We're all familiar with bird's nesting or medium length, kind of the ratty looking chips, if we were. Those left 2 pictures on the slide here show the conventionally poor chip formation. The perfect chip, right, is going to be on the right there. That short chip that evacuates consistently is the same size, or relatively the same size, and allows consistent evacuation through the drilling process. Drilling is probably the most, we'll call it inconsistent process, because you can't visually see it. So being able to make a consistent chip translates it from a hard process that you're not able to actually see what's going on to a process that you feel confident in applying to your parts. When we look at chip form is a indicator of not only how the performance of the tool is going to last due to the right cutting parameters and actually right mechanical forces being applied, but the actual torsion built up in the drill itself. Poor chip formation can lead to inconsistent torque or torque spikes as you're drilling deeper, right? If we're drilling a 1x diameter hole or a very shallow hole, the torque values are going to be pretty consistent. We're not too concerned about chip evacuation. Even long chips are going to evacuate on a short bore. But as we continue to go deeper into a bore, the importance of a constant torque being presented on the drill is even more vital. So good chip formation will allow consistent evacuation from the start or the shallow portion of the bore to the deepest portion. This graph that you're seeing right now, blue is a constant torque process. This is something that's going to be exemplified in a one hole or one peck process, right? One shot, no pecking. And then the orange graph is a drill that's not performing to the quality of you're reaching a certain depth, right, as we continue along. And after that certain depth is achieved, now we see drastic increases in torque. When we see drastic increases in torque, this will generally be a symptom or a symptom before a drill failure, to put it mildly. As we see these giant jumps, we're applying much more mechanical force onto the drill body itself, and we increase the likelihood of a catastrophic drill failure. This is something we absolutely must avoid if we're machining high value parts. Looking at titanium compared to common materials, right? This would be kind of a generalized breakdown on a scale of looking at the materials that we're all used to machining, right? Yellow is going to be your steels. That's a generalized category, but we'll take that as an average of the steels. Obviously, we have high and low end there. Aluminum coming in, and then red is titanium. This scale is supposed to show and represent just the major differences that we see in titanium across the board. Much more of a tough to machine material that is way more prone to catastrophic drill failures, mill failures, turning operations. The specific strength of the material is quite high, the elongation at break, fatigue resistance. These are all factors that parlay into, number one, the geometry being used on the tool, but also give you a higher likelihood of having a poor condition if you're not applying the right tools. Thermal conductivity. This is one of the most important factors when we start looking at drills in general. As mentioned before, drilling is going to be in total internal operation. We're not going to be able to visually see this, nor will the chips be able to just fall away from the part. We have to manually remove the chips from the bottom of the hole to the top of the bore in order to actually move them away. Why does thermal conductivity play a part in this? Well, where all the heat should be going is into the chip. Problem with materials that have low thermal conductivity is the material doesn't want to absorb the heat. They want to deflect the heat and have it sink into the drill itself. When we look at carbide as the median of what we're making these drills out of, carbides can really be thought of as kind of the Rice Krispie treats of tooling, right? What I mean by this, Rice Krispie treat has two major components, right? It has the Rice Krispie component, the hard, we can think of those as the tungsten and the carbide tungsten particles, and then the binder or the marshmallow, right? The marshmallow in this sense would be cobalt. It's the most common binder used. And that binder holds all those carbide tungsten particles together and makes for a stable, homogeneous unit to make a tool out of. Well, when we look into the heat properties of those two materials, the cobalt binder has about, it's under half the thermal or the melting point of tungsten. We're looking at about 1400 degrees centigrade for the melting point of cobalt, and tungsten carbide is going to be about 3600 centigrade. So what this means is if we're not putting all the heat into the chip and we start absorbing the heat into the drill itself, we run a much higher risk of melting the cobalt or the binder. At the point that we start plasticizing or making that binder soft, then we're going to see the resulting drill failures that we're all familiar with, the chipping, the wearing down of corners, and general degradation of the tool. Looking at this graph, right, carbon steels, very nice thermal conductivity. When it comes down to it, they like to take a lot of heat. Stainless steels are high temp super alloys, as we're moving into that there, a little bit less, but even compared to the high temp super alloys, titanium has a lower thermal conductivity, right? What this means, it really doesn't want to take heat. It wants to maintain a constant temperature. Optimal heat evacuation as we get into the cutting edges of a drilling operation itself, right? The workpiece should only absorb a little bit of heat. The tool should be under about 20%. If we look at the generalized heat graph on an optimized chip, we don't want to reach anything more than about half the melting point of cobalt. We see that being portrayed right in the center there at about 700 degrees centigrade, from the point of all the other heat being pushed into the chip and evacuated. When you're dealing with a material like titanium that doesn't want to absorb the heat, what you end up having is a lot more heat pushed back into the tool, making it more unstable. So this is where it comes into a very important factor of having the right cutting geometry to actually shear that plane while maintaining consistent tool pressures. As we look into titaniums as a generalized family, right, we can break down the machinability and again show the decreased machinability of titanium alloys. When we're looking at heat-resistant superalloys, our Inconels, our Hastelloys, or WASP alloys, they're around that same average, but have a little bit greater top-end machinability compared to steels and stainlesses that we're all used to machining on a daily basis, right? These fall much under that category. What's interesting about titaniums, though, is they fall into even a little bit of a subset category when it comes in. Not all of the average machinabilities for every type of titanium falls directly in the line that we see. We end up separating these two into the most common categories of titanium. Commercially pure titanium, or CPs, those are typically going to be your grades under 4, so 1 through 4. Then you have grade 5 and above. These are going to be our alloy titaniums. Typically, the alloy titaniums have a little bit greater strength, right, due to their alloyed components, and a little bit better machinability. Looking at it from a drilling standpoint, you can't have one geometry parlay across a family of titaniums. Commercially pure titaniums, much more gummy, much more sticky, have a real tendency to build up on to the drill itself, weld itself, and present a gummy condition. Alloy titanium is much stronger. You have to have a little bit different of a cutting geometry to approach that stronger tensile strength material and create a chip effectively. But this is something that our R&D lab spent a lot of time to develop one drill for both these materials. What we figured out is we weren't able to give a satisfactory solution to our customers who specialized in grade 5 if we were kind of meeting in the middle. So we separated our drilling lines, going for an alloy titanium and a pure titanium. As we look kind of the differences, right, grade 1 through 4, these are going to be the most likely materials we're going to run into in the bone plate category. Typically, these are not going to be an external part. We may find some, call it consumer goods that are made out of grades 1 through 4, but typically these are going to be implantable plates used for not only their biocompatibility, which matches with grade 5, but also the slight flexibility that grade 1 through 4 allows. A little bit of a more forgiving material. As we move into grade 5, right, we'd say this is going to be a little bit harder, slightly stronger as it's alloyed, and more for rigid components, whether this is going to be fixtures on the medical side, and fixture components, as I mean screws, stems, actual shoulders or knees, joint implants, or on the side of aerospace where you have that need for a much stronger material, a little bit greater heat resistance. Where are we at today, right? If there wasn't a problem, we wouldn't have found a solution for it. So we started looking at the commonly viewed drills in the market today, right? And basically all general purpose or material specific, even when it comes to the high temp superalloys, they don't match up to the point of the titanium products needed. So running a variety of drills, we started looking at the common problems seen on drilling titanium. Pictures on the right here show a few of the most common areas, right? We'll start at the top and we'll start seeing some corner and margin wear. This is where a lot of the heat is being built up as the drills reach deeper depths. With greater heat, we have a greater chance of that material welding onto the material. That picture to the top right corner there really shows a exaggerated and pretty much borderline catastrophic failure coming to that drill, where a lot of the titanium material has actually adhered itself and bonded itself to the drill. This throws off your runout, it throws off the geometry put on the drill, and you no longer have an optimally running tool. That middle section of lines, these are going to be heat wear symptoms, right? On one side, we have buildup material that has actually extruded itself over the cutting edge or up through the flute and welded past the coolant holes. Now we're going to have a non-equal coolant pattern. We're going to see heat raise greatly as we go deeper in that bore, resulting in a lot of the effects we see on those right two on the middle row. With that corner wear, this is a common symptom to see with titanium drills, where due to that heat, we may not experience a chipping, we may just experience a complete wear down. That binder is becoming so soft that it's becoming almost malleable. We're wearing it down completely to now the point we're changing the geometry of that tool. Geometries of the tools are the most important subset when it comes to actually the shearing technology. So as soon as we start changing not only the rake angle, but the actual cutting edge itself, we start drastically seeing reductions in tool life. The bottom there, we have a perfect example of a changing torque, a force that's not being portrayed to the actual tip of the drill, and we see substantial wearing on the tip as well as the corners, and then subsequently on the flutes. Why that picture on the bottom right-hand corner is very important is once we make a chip, we have to be able to evacuate it. And a common sign of failure that we saw in the most up-to-date drills on the market were adhesion of material, not only on cutting edges, but on the flutes. So we'll come back to this and address that point later on how we actually overcame that obstacle. So the innovation, addressing those most commonly seen failure points with the drills, we designed two lines. On the left, you'll see the ATC, alloy titanium cool. On the right, the PTC, pure titanium cool. These share many of the same features, but in different geometries and designed for that material in specific. If we start at the top, we look at cooling, right? We talked about thermal conductivity. We talked about keeping a material at a constant temperature, as well as the tool at a low temperature. To be able to add this in, we took our patented kidney-shaped coolant holes and we added some special exits. So actually grinding directional exits into our coolant channels to make sure that the coolant leaving the drill is being directed to where it's needed, the cutting edges. We start looking at those center four, 3 through 6, right? And this really comes into cutting edge and chip control right off the front. That front portion of the drill is going to be not only responsible for creating the chip in size, but also breaking it. So by being able to have specific edge geometries designated for pure versus alloy, depending on the need there, and protections, we're able to manage heat a little bit more effectively. Taking into the flute 5 and 6, the lands, right? After that chip is then cut from the material, we need to be able to manage it, make sure that we're not rolling over, seeing any of that major margin wearing, or a chip that becomes out of control. So we move into the slight portion behind the cutting edge. After that portion, the last slide we saw was the piece of material welded onto the actual flutes itself, packed in there, which will obviously cause blockages from future chips and an increased torque. So the way we came about this, every one of the drills you see on the market for whether ATC or PTC coming from Micron Tool, we take great care in polishing our flutes. The drill isn't finished when we make the cutting geometry. The drill is finished when those chips are evacuated all the way out. Without polished flutes, without the extraordinary care we take to lower the friction of the fluting themselves, we wouldn't be able to effectively evacuate the chips. Starting kind of diving deeper into each one of those components, when we look at the thermal conductivity, it's been a repeat theory, and it's something I want everyone to take away when they start really diving into optimizing their processes for titanium, is the cooling. This is an example of the effectiveness of our cooling channels. As we see here, left side, specially designed coolant channels, again, are kidney shaped, utilizing as much internal volume of the drill itself without a degradation to stability. And on the right, are conventional drilling holes or just round coolant holes. I show this video to many people and they always think that I'm speeding one up. I promise you this is not the case. This is an actual lifetime perception of the coolant channels in a real world environment, about 60 bars. So we can figure a little under 1,000 PSI coolant there, right? What this means, we're transferring about 4 times the amount of coolant to the cutting edge. This means we're able to maintain the cutting geometry better by maintaining a lower temperature at the tool itself. I saw there was a couple questions before this webinar started, so I wanted to address it throughout this time we had together. Is there a difference between cutting oils? Right? Generally, as we look into pressures versus types of coolants, we have an optimization zone of what I would consider under 2 millimeter drills, anywhere between that 1,000 to 1,200 PSI mark is generally where we want to see those tools running, whether you're in emulsion or oil. When you get to 3 millimeter and above, I'd say you can get away with a little bit less, probably that 800 to 1,000 PSI mark. 4 millimeters and above, we may be able to get down to about 600, but a good rule of thumb across the board is 1,000 PSI, around 70 bar is where we want to be shooting for, no matter if you're running a small drill or a larger drill. When it comes to type of coolant, this is an example. It's a case study with a 4 millimeter version of our ATC, drilling in grade 5, one shot, where we were able to look at 2 different types of chip formation. On the left, we see an emulsion. On the right, we see an oil. Typically, oils lubricate better. All right. Water-based evacuate heat a little bit more. So what we're seeing here is the water base is pulling the heat away a little bit more effectively, causing that chip to form at a greater rate. On the right side, where the oil is coming in and not transferring that heat quite effectively, we see the material staying a little bit more malleable and causing that rippling of effect. To treat or diagnose a situation like we see on the right, it's been my experience to increase feed in relationship to the running parameters to be able to give it a little bit more of a embodiment and then break that tool or break that chip more effectively. Drill jamming, right? This becomes a key factor as we're working down the list here. We've tackled coolant, we've tackled edge geometry and preparation of the corners, the margins, the webbing, as well as the internal fluting. Then we look at drill jamming, right? What is drill jamming? Why does it come into play? If we were maybe putting out a drill that was only going to be drilling shallow holes, this wouldn't be a big concern for us. But the consequence of drilling deeper is you have that possibility of increasing torque, having chips be stuck in the bore, or having the material actually shrink upon itself, right? As you're drilling, you're transferring heat to the tool, the chip, and the material of the workpiece itself. If you add heat to the workpiece itself, typically you're going to see an expansion of that material, right? The case is the same in titanium. If you add heat to the material, you'll see a slight expansion. As you drill past that point, the material may return to its natural state. At that point, you could see a hole that's undersized nominal dimension. So it becomes important to not only cool the drill, but also the workpiece in a consistent area. We also combat this by specialty geometry of providing a back tapered situation, special pressurized margins to be able to cut through, but not allow that material to ever come back and make contact with the drill after it's made or gone past that portion of the bore. So manageable chips, now we're going to be getting into a case study, a little bit of a situation here on looking through a case study of traditional, left, right. Okay. This is the key, this is the type of chip you should be seeing from the ATC family of drills. This would be the same type of chip I would show and say, okay, you want this type of chip in 1018, 4140, or 316 stainless. The idea was to take something that we weren't able to achieve, that sort of chip, and have it on the market where we can consistently perform that type of chip. After my first time running one of these drills in the field, I came home giddy as a school kid, and I had a bag full of chips that looked like that. My wife at the time was looking at me like I was a little bit crazy. She laughed. She goes, "What do you have?" So I have a bag of chips, because I was so impressed by the capability of these chips to have a consistent formation across the board that I would see with other commonly drilled materials. So how do we achieve that? We've touched on the basis throughout this presentation, and we've also seen an increase in surface finish due to good chip formation. So not only is good chip formation going to be parlaying itself through evacuation, reliability of tool life, consistent hole size because you're not rubbing in that, but it's also increasing the quality of the bore. So we see here a very fine surface finish to the point where you could almost get away without a reaming operation if you have a low surface finish call out. This chart right here, we're showing RA in micrometers, 0.2, to say 0.3 micrometers. We're in that range between 8 and 12 RA. This is going to satisfy many of the call outs that we have on the prints and the parts we work on. A little bit of a video here showing longer tool life, right? The tool is only as good as the value it adds to you as the customer. And as we see here, the drilling process must be consistent not only at hole 1, but at the end of hole life. So we took something in the market as a general purpose, and we wanted to make it specific. We made it specific, but we also wanted to add tool life and productivity to you. Touched on at the beginning of this presentation. If we can't offer a reliable solution to you, then it's not really of value. So we took this tool and we wanted to have it meet the capabilities that we're seeing out of stainless steel. So in this example, we're running water soluble coolant. We're running it 1 shot, right? Now I say 1 shot as in we're not drilling anything from the 3 times D pilot to that 10 times D with PEX. It's 1 shot from that standpoint. Each one of these holes, as you noticed at the beginning there, do actually have a pilot bore put in place first. That's able for that small diameter drill to have a starting point and find good position. We ran this test, 4,500 holes. At that point, we found the tool life, the qualification of the tool, and we were quite happy with where we'd reached performance-wise, right? If we look at the comparable wear of a tool at 4,500 holes in titanium compared to a hole after, or a drill after 4,500 holes in stainless steel, we're seeing very similar wear patterns. In addition to that, this perfect highlight, this is the bag I came home with, showed my wife, of the short chips. It's, to me, one of the most outstanding factors of this drill is the performance of the material, that we see consistency. Without that consistency, we're not going to have reliability. We're going to have inconsistency of holes, and we're going to have drill failures. So that right there, those small chips, show a drastic leap forward in technology, in my opinion. Right here, I wanted to highlight this wear pattern. This is a good example of wear across the board in any drill, in my opinion, whether it be alloyed steel, stainless steels, or here in titanium. But these are all good factors for everyone to look at. And as you have can download a copy of this, you can save this view and take a look as kind of a reference point of what a drill should be wearing at. Obviously, there's many factors that go into drill wear outside of the tool itself, but assuming that you have good work holding, good spindle, good tool holding, we should see consistent wear. So every tool is going to wear at some point, but as I highlight here, across the cutting edge, right, we need to see consistent wear. 4,500 holes, I would say this is a superb example. We have very little wearing at the point itself at 0 surface foot or 0 speed. As we move across the edges, we have a consistent amount of glinting across the S, the radial point, the cutting edge, and the corners. The most wear indicator of heat we see is right on the corners, but no degradation on the edges themselves. Looking at the side of the drill, or coming into the main flute here, we see a little bit of material wear inside that main flute as it's taken a lot of wear and tear. The corners itself look pretty good. You do have a bit of build-up edge on one corner, to be expected, but moving over to the right here, our margin is purely intact. Again, we see a bit of build-up edge starting to present itself on the glinting here. Overall, the margin is still in spec, in the same basic size that it started as, and we're not seeing any wear past the margin, which is a key indicator of failure coming in a titanium drill, when we start extruding material past this margin and getting actually to the drill diameter back here, the primary relief on the margin. In review of these two lines, we showed that case example from the ATC drill. The ATC is on the market. We have a 3 times D pilot, a 6 times D drill, and a 10 times D drill. For diameter range, we start at 1 millimeter. We go to 6 millimeter in metric, 1/4 inch in fractional. We have increments of 50 microns and 100 microns up to 1/4 inch from 4 millimeter. The coating is proprietary micron tool coating called S&P. You'll be noticing a bronze coating on the tip of the drill, and I say the tip for about the first 3 to 4 times diameter. It will appear bronze in color. Feed rates, that 150 to 200 SFM seems to be a quite happy spot for this tool consistently, given that you have the right coolant and pressure. Feed rates anywhere from 1 to 2%. If you're running oil, if you're receiving that harmonica, or not harmonica, accordion chip, then you would be increasing that feed slightly, but a 1 to 2% of diameter is a good place to start. Key factor for this drill, it does drill in one shot. If we're looking at a system, a couple of you guys sent in questions for LFE or HFE or HFT, high frequency turning, low frequency vibrations in your citizen or FANUC controls. Would I recommend utilizing a process like that with these drills? You're going to have good chip formation of this drill in one shot. So my recommendation would be that you don't need to run a process like that for that exaggerated PEC cycle. If we're dealing with extraneous circumstances where, for whatever reason, we can't break a chip, we have ran those systems with success. But for the ATC and alloy titanium, this drill was designed to make small chips consistently to depth at one shot. If we add a PEC cycle in, we're adding a lot more wear and tear to the amount of contacts we're having with the tool, and I would expect to see decreased tool life due to the increased wear, particularly at the point and the corners of this tool. Moving over into the PTC, we'll notice that the size range matches up diameter-wise. The size of lengths vary a little bit. We have a 3 times D non-chamfer drill and a 6 times D drill. This is the complete line of this tool. It's being released as such, and we're seeing this in the market to match a certain need. We look at ATC. ATC is a family right now to 10 times D with plans to extend longer to match our other drilling lines. PTC stops at 6 times diameter, and we have no plans to extend this. A common question I get is, why is this so? Pure titanium applications are generally dealing with bone plates or shallow holes. In the case of shallow holes or thin-walled plating applications, we don't need to take that drill any further past that. You're generally not seeing large components or deep bores generated in pure titanium. So this family stops at 6 times D. Where we get into the effectiveness and where I would apply LFV or HST in an effective way would be a chip break cycle. As we see here, the process for grade 2 and grade 1 in some circumstances, we do have a necessity to actually break a chip. As stated before, grade 2, that pure titanium, much more gummy. It really doesn't like to break a chip. It doesn't like to be controlled. So as we bend over the chip with a cutting edge, we need to actually remove ourselves from the cut to cause that drill breakage. Excuse me, not drill breakage, chip breakage. From that standpoint, if you're running a HFE on one of these tools, I'd find it with great effectiveness. Grade 4, most of the time, given the right coolant and pressure, we can get away without running a PEC cycle. If you don't have, a low frequency vibration or high frequency turning program on your machine, a G73 PEC cycle will work just fine. We recommend at about 15% diameter for each one of your PECs with a subsequent retract of 10%. If anyone is going to be visiting EMO this September, we will be exemplifying or exhibiting both these tools. Feel free to stop by, communicate with our staff there. They'd love to show you these drills, show you some more videos and literature to go along with this product. Greatly appreciate your time and attention. Now I open it up for any questions that were submitted to Dennis during the presentation itself. My contact information's here. Like I said, I greatly appreciate you guys taking your time over your lunch break or early afternoon to sit with me to hear about titanium drills. If you have any questions, you'd like to reach out to have a conversation in person or have one of our regional sales managers stop by and do a presentation, technical presentation on these drills into more depth or even with a greater group in your company, feel free to reach out to me. My email, clive.comlenik@micron.com, is in the bottom right-hand corner, along with my phone number. I'd really like to hear from you. I'd like to meet you in person and see your applications. So thank you, and I'll turn it over to Dennis for the Q&A.
Thanks, Clive. We don't have any new questions coming in, so we'll give them a few minutes to get their thoughts together. If anyone is out there and wondering how to submit a question, I do have a quick kind of guide that I can show you as to what it will take. You should have a screen with a GoToWebinar control panel on it that looks something like that. And we're gonna just take a closer look at that. This button here that just will close the window if you click it, collapse it if you wanted to do that. But just click it again and it'll come back up. And the handout section has a copy of Clive's slideshow presentation that he just presented in a PDF form. You can look at it, find it in that side panel and click on the link that's there and it'll open up a browser window and you'll be able to download it from that browser window right onto your desktop. But for questions, this is where you go for the questions. You can type your question in that panel right there. And then you just need to hit the send button. And as soon as you do, it appears right there. So with that, if anyone is out there who has a question, this would be a good time. Were any of the questions that came in advance like difficult or more common questions that you're used to fielding, Clive?
Yeah, so like I said, I tried to adjust the presentation a little bit from what we had originally to address some of the questions we had. Some of the questions discussed hardness of materials. I can take time as we're waiting for questions to come in to answer that. The question was, what type of hardness do drills or tools reach up to? It's kind of I'll say it's a generalized question that I'll break into a few components. When we look at hardnesses of titanium, most titaniums are going to be measured on the Rockwell B scale. and anywhere between 30 Rockwell B and 90. So the hardness of the materials generally aren't the challenge. It's the malleability, it's the low thermal conductivity, which really portrays a problem drilling this material. When we get into more common materials, your participation hardened stainless steels, your tool steels, it's a wide array. Stainless steels, we're generally seeing anywhere between 38 Rockwell C and high 40s. When we get into our tool steels, that can be upwards of 60 Rockwell. Titanium drills, this whole line, let me take a little bit of time to mention, this is really only for titanium. I wouldn't run this tool in stainless steel. I wouldn't run this tool in hardened tool steels. We do have other lines that address those materials more specifically and are designed for dealing with the properties inherent with those materials.
Okay. I'm still waiting. Is there some other aspect? I mean, this, how long has this been out on the market and available?
So ATC was officially released at the beginning of the year. We've seen it come into the market this first half. PTC is officially being released at EMO. So a little bit of a sneak peek, a preview, if you were. I know the Hollywood writers are on strike. I am not, still working, I'm out there, and PTC is excited to be released here in the upcoming months. So
if somebody is interested, though, they'd be able to talk to you about it and give a timeline on how soon they'd be able to test something out.
Yeah, absolutely. So stock is being built. We have many tools already on the shelf. For ATC, we have a full array of tools ready to be put in the marketplace. Like I said, some time myself introducing in the market, testing it before I even take it to my customers, something that I find very important. Before I take a tool or work on an application, I have to be able to run it, feel it, look at the chips myself. So the ATC line, the alloy titanium, is ready to rock and roll. If anyone's ready to test or would like to reach out, we'd be more than happy to come in and do a presentation.
Cool. We are getting a couple of questions now. Let's see, I'm just going to read this off to you so you can just respond. Did you happen to run your test at the APT, I'm sorry, higher surface feet per minute to reduce bug? If so, how much did it affect the tool life?
Great question. So I think, correct me if I'm wrong, if it comes in again, but did we run our drills at higher surface foot, higher speed than the 200 surface foot that we were calling out? We did run some, we'll call it extreme testing on the drills themselves at higher surface foot. What we did figure out is there's that balance point between productivity of the tool as well as tool life. Running higher, we saw a slight degradation in tool life compared to what we were seeing at optimized parameters. But there's also many considerations to look into there. If we can consistently reduce cycle time by running faster, is it worth the slightly reduced tool life possibility? Parameters in any of our catalogs, any of our books, they really are supposed to come out and offer a good starting point for optimization or the good balance between tool life and performance. What I run into even on smaller sizes, sometimes at 200 surface foot on a drill of 2 millimeter and below, we may max out many spindles. So there's always consideration taken into the parameters put into the book need to work for the majority of people in the field. And if we're calling out very high surface footage on a 1 millimeter tool, people may get the idea that the drill may not perform at a slower speed. I find that 150 to be kind of the bottom end of like performance. There is a degradation on the backside. We can look at performance of parameters as a bell curve. Too slow or too light on feed, we're gonna be rubbing the tool and we're spending too much time in cut. Too high or too hard on feed, and we're gonna be putting too much torque or too much heat into the tool. So the parameters that we're at, they seem to be the best in-world examples that we were able to come up with from our R&D lab and then make a confident assumption for our customers.
Yeah, the same individual, Brad Rimmer is his name. He's asking what type of tool holder did you run the drill in?
Yeah, thanks Brad for asking the question. We test in generally two types of tool holders, hydraulic and RegoFix PG systems. They're generally the most consistent across the board for us. And when we're doing our testing, we generally try to stick with those. When it comes to tool holders on the market, it's a very good question. I generally recommend hydraulic as my first option. I'll get into RegoFix, Shrink Fit as that second tier, If I find myself in the ER collet realm, which I do quite often, I prefer an ultra precision sealed collet. So ultra precision with run out of less than 2/10 is what's recommended across the board for our product line.
Okay. So I'm not sure if this was part of the first question or not, but there was like a partial question from Brad, and I just asked him if this was part of the first question, but he's not sure if he was asking about a built-up edge. So it might have been related to the first question.
Built-up edge with the increase of speed. Was that going off that question, Dennis?
Yeah.
Yeah. So as we see an increase of speed, if we're seeing we'll call it a detriment of coolant, right? If we're at moderate parameters, the increased speed will add more heat to the material that's being generated as well as the tool. So you have an increased tool temperature and internal temp, which is going to make it easier for that material to adhere. So build up edge, as you go past that speed point, we are seeing, we did see greater material adhesion, right, as you get into longer tool life. So.
All right, and that was, you just responded. If
okay, good.
Anyone else out there got a question, as we still have some time. And we can wait a few minutes, so if anyone does, you just type it in and submit it. So you're traveling the road quite a bit right now, is that right, Clive?
I am. I'm enjoying, I travel anywhere from Maine to Texas, supporting our team on the East Coast here. I get to bring home, like I said, bags of chips to share with my wife and talk about my stories of the road. She's always happy to hear about them. But enjoying seeing new applications. Right now, we have a pretty exciting time in American manufacturing, and it's good to be on the road in different areas, different regions to see what's up and coming, what they made success with in the past, and how they're translating into the future here.
Brad actually is asking if you tried a greater emulsion.
Great question, Brad. In R&D lab, when we were running our testing, we generally run at about 8 to 10% concentricity. We try to keep it there. We did not run at, say, a 14% or a 16% concentration. I've run it in the field before. What you typically see at a greater concentration, call it 14% and above, if you're really running into that, is more similar chip formation to oil, right? With a more of coolant, less water in it, then you're losing a little bit of that performance of the actual water being able to remove the heat effectively. So the higher concentration you get, the more similar it's going to be to that lightweight oil.
So how long have you been out on the road right now? These, like in this past month, is this like is it get the busy season, or is this a slow part of the season?
Every season's busy, Dennis. It's a beautiful thing of our job. This week, well, I think about this month, I'll be at home. Been home 6 or 7 nights, so it'll be all right.
All right.
At least the weather's good. Or, we're not dealing with snowstorms quite yet.
All right. Well, I don't want to keep anyone from their lunch if they're at lunch and eating while watching this. If there are no other questions, we will just wrap it up by just mentioning that you can reach Clive at that his contact information, which, by the way, we'll make available on our website when we post a recorded version of this webinar. Later today, you'll either see it or first thing tomorrow morning, and you can also download the slideshow presentation in PDF form from there as well. And with that, I want to thank Clive and Micron Tool for working with Cutting Tool Engineering to present this webinar. And I also, as always, thank the audience for attending today's event. Anything else that you would like to add, Clive, before we wrap this up?
I'd just like to thank everyone here. It's always nice to communicate with people, even on a virtual sense, and share experience that we're running into. I love hearing the feedback from our customers. It makes everyone better. So Dennis, thank you very much for providing us with this platform, for sharing your time and Cutting Tool Engineering's time with this, putting the presentation together. Very well done. And for anyone out there who's interested in learning more, feel free to reach out. I'd love to come visit you or set up a meeting with one of our employees.
That's it's a good point. And if you think of a question after we close the event, you can still submit a question by sending it directly live or to me at Cutting Tool Engineering. My email address is right on the website, or if you want to write it down, it's dspaith@ctemag.com. Again, thanks everyone. Appreciate it. We'll let you get back to your lunch early or get back to work a little ahead of time. Really appreciate it. Very well done, Clive. Thank you.
Thank you, Dennis. Appreciate it. Thank you, everyone.